Hey, welcome to the Explainer. Today, we're going to jump into a tool that's, well, it's everywhere in science and engineering. It might just look like an arrow, but trust me, it's got the power to describe everything from a baseball pitch to a planet's orbit. So let's get into it and explore the world of vectors.
All right, let me start by throwing a little puzzle your way. If I tell you a car is zipping along at 100 kilometers per hour, can you tell me with certainty where it's going to be in 1 hour? The thing is, you can't. Not really. You know how fast it's going, but you're missing something huge. Is it heading north, south, straight into a lake? You've got no idea. And that missing piece, that direction, well, that's exactly what we're talking about today.
And this is where our hero of the day comes in. The vector. A vector is the simple, brilliant answer to our problem. Think of it as this neat little package. It bundles two crucial bits of info together. A magnitude, which is the how much, our 100 kilometers per hour, and a direction, the which way, like due east. It's the arrow that shows us the way. Okay, so if we really want to get what makes vectors so powerful, we've got to kind of take one apart, right? See what's inside. So first things first, let's draw a really clear line here. Over on one side, you've got scalars. Super simple. A scalar is just a number. It's your age, the temperature, the speed of that car. But on the other side, that's where vectors live. For our car, the vector would be its velocity, 100 kilometers per hour, east. You see that difference? It's huge. One is just how much, but the other is how much and where to. So let's look at the anatomy of a vector. What are its parts? And yeah, you'll see a few Italian terms here. They pop up a lot in classic physics, so it's good to know them. First up is its magnitude, or modulo. That's just a fancy word for its length. How long is the arrow? Then, of course, you've got its direction. Now, to actually do math with these things, we break them down into components. Think of them like the vector's shadow on the x and y axes. And last but not least, we have these super useful little helpers called unit vectors, or versori. Their only job is to point. That's it. They're like little signposts. All right, so we know what a vector is, but the real fun, the real magic, starts when we let them play together. Let's open up the vector toolkit. Adding vectors is actually way more intuitive than you might think. Imagine this. You walk 3 blocks east, and then you take a left and walk 4 blocks north. How would you figure out the straight line distance from where you started? Well, you do exactly what's on the screen, the tip-to-tail method. You draw your first vector, and right where it ends, you start the next one. The final result, that new vector, is just a straight line from your original starting point to your final destination. It's literally the shortcut on your mental map. So simple. Okay, so what about subtraction? Believe it or not, it's even easier. See, subtracting a vector is just a clever trick. It's the exact same thing as adding a vector that's pointing in the complete opposite direction. So instead of subtracting east, you just add west. That's it. Done. Okay, hold on, because multiplication is where vectors get really cool and kind of weird. Why? Because there are 2 different ways to do it. First, you've got the scalar product. This one answers a simple question. How much are these 2 vectors pointing in the same direction? It's like, imagine you're pushing a heavy box. The more your push lines up with the direction the box is sliding, the more effective it is. That effectiveness is a single number, a scalar. But then you have the vector product. This one is totally different. It doesn't give you a number, it gives you a whole new vector. And this new vector is crucial for anything that spins or rotates. Think about using a wrench. We're going to come back to that idea for sure. So we've got our toolkit. Let's actually build something with it. Let's see how these little arrows become the language we use to describe, well, pretty much anything that moves. Everything has to start somewhere, right? And for motion, it starts with the position vector. Just picture a map with a big "you are here" dot on it. The position vector is nothing more than an arrow from the map starting point, the origin, pointing right to that dot. Its entire job is to say, hey, the thing is right here. It just nails down its location in space. Okay, but things don't usually stay put. So what happens when that dot starts moving? Well, its position vector has to change too. And the rate of that change, both the speed and the direction, that gives us the velocity vector. This is the vector that finally answers our car puzzle from the beginning. Its length tells you how fast, and its direction tells you which way. But wait, we can take this one step further. What happens if the velocity itself starts to change? You know, like when a car stomps on the gas, hits the brakes, or even just takes a turn. Any of those changes in velocity, that is what the acceleration vector describes. And this is super important. Acceleration isn't just speeding up. Changing your direction is also an acceleration. Any change to that velocity vector counts. But here's the thing. Vectors aren't just about motion. They're just as powerful, maybe even more so, for explaining why things stay perfectly still. So let's shift gears and look at the physics of balance, forces, and what keeps a bridge from falling down. Think about a game of tug-of-war, right? If both sides are pulling with the exact same strength, that rope in the middle isn't going anywhere. That's equilibrium in a nutshell. In the language of physics, it just means that if you add up all the different force vectors pushing and pulling on one spot, they all cancel each other out. If you drew them all tip to tail, you'd end up making a closed loop right back where you began. The net result, 0. Okay, that's easy enough when everything is happening at one single point. But what about something bigger, like a seesaw, or trying to turn a stubborn bolt with a wrench? The forces are being applied in different places, and that brings in a whole new possibility, rotation. So, how do our vectors deal with spinning? The answer is an amazing concept called torque, which you can just think of as a twisting force. And how much torque you get depends on 3 things: how much force you apply, the angle you're pushing from, and, this is key, how far you are from the pivot point. That distance has a name. It's the lever arm, or as you see here, the braccio di una forza. And remember that vector product we talked about earlier? This is its time to shine. It's the exact mathematical tool you use to calculate torque. Okay, so let's put it all together. For a big object, like a ladder leaning against a wall, to be perfectly stable, what we call rigid body equilibrium, it has to satisfy 2 rules. First, all the straight line forces, the pushing and pulling, they all have to add up to 0. That keeps it from sliding away. And second, all the twisting forces, all the torques, they also have to add up to 0. That keeps it from toppling over or spinning. It has to be perfectly balanced, both linearly and rotationally. No sliding and no spinning. So think about where we started. A simple question about a car. And where did we end up? Figuring out how a bridge stayed standing. All with this one simple idea, the vector. It's given us a completely new language to describe the world. At the end of the day, these arrows aren't just some abstract thing in a math textbook. They're like the universe's hidden language. From the pull of gravity holding planets in orbit, to the wind pushing on a skyscraper, all the way down to a kicked soccer ball, vectors are there, quietly explaining how it all works. So I want to leave you with a final thought, a question for you. The next time you lean against a wall, or watch a leaf flutter down in the wind, or even just turn a doorknob, now that you speak this language, what simple, everyday thing can you look at and see in a totally new way? Not just as something that happens, but as a beautiful, elegant dance of invisible arrows.